The definition of acids and bases we've worked with so far is called the Arrhenius definition of acids and bases. In this lesson, we'll learn a new definition of acids and bases called the Bronsted-Lowry definition. We'll learn that this helps us think about substances acting as acids or bases in a slightly different way. So what are Bronsted-Lowry acids and bases? Let's take a look. So, first of all, the definition itself tells us that Bronsted-Lowry acids donate H. That looks pretty much like what you might expect. The Bronsted-Lowry base definition, though, starts to look different. You'll notice you don't see any hydroxide there. Instead, it says it accepts H pluses. So Bronsted-Lowry acids donate H pluses or protons. Bronsted-Lowry bases accept H pluses or protons. Let's look at an example of each. So let's say we have HF, which you probably recognize as hydrofluoric acid, which is an acid you're using, but thinking of it as a Bronsted-Lowry acid tells us that it has to donate a hydrogen. And that means there's something there that accepts it. So whenever we look at Bronsted-Lowry acids and bases, we typically react them with water and see where our hydrogen ion goes. Well, in this case, since we know that our hydrogen is going to be donated, that means that HF is going to give it up and H2O is going to accept it. And what that means we get as products for our Bronsted-Lowry acid base reaction is F minus because the HF lost a hydrogen, and H3O plus because my water gained a hydrogen. Remember that hydrogen ions are positive, and that's why HF, which was neutral, became negative when it lost a hydrogen ion. And H2O, which was neutral, became positive when it gained a hydrogen ion. So there we have our Bronsted-Lowry acid. So I'm going to label that our Bl acid. All right, now let's look at a Bronsted-Lowry base. One example of a Bronsted-Lowry base, probably the most common one, is NH3, which is ammonia. When we react it with water, we know that because it's a Bronsted-Lowry base, it's going to accept a hydrogen. That means that the hydrogen is going to come from water and be transferred over to ammonia. And so when ammonia gains a hydrogen ion, it's going to become positively charged, and it's going to go from H3 to H4. So we get NH4 plus. Now, what's left behind? Well, H2O, right, gave up a hydrogen. So it's going to become negatively charged, and it's going to have just one hydrogen instead of two. So that's hydroxide. Now you might understand why NH3 is considered a base, because when you put it in solution, even though it itself doesn't have hydroxide ions, you can see that it actually does put them off into solution. Okay, so that means that NH3 is our Bronsted-Lowry base. All right, something interesting to notice here though. In the top reaction, water accepted a hydrogen ion. So in the top reaction, actually, there's a Bronsted-Lowry acid, NHF, and a Bronsted-Lowry base in terms of water. So here we have a Bronsted-Lowry base. Why? Because one of them accepted a hydrogen, that's water, and one of them donated it. So the fact that our water accepted a hydrogen makes it a base there. In the bottom reaction, however, our water donated a hydrogen. That means down here, it's acting like a Bronsted-Lowry acid. So that's a little different than what we've seen before with, say, the Arrhenius definition of an acid or a base. We're used to thinking of a given compound as either an acid or a base. But we can see here that based on what you mix water with, sometimes it's going to accept a proton, sometimes it's going to donate a proton. And that makes it what's called amphoteric. So H2O is amphoteric. And that means it can act as an acid or a base. Acts as acid or base. Okay, some other vocabulary that you should be familiar with when it comes to Bronsted-Lowry acids and bases are conjugate acids and bases. Here's the trick. If you have a Bronsted-Lowry acid, after it donates a hydrogen, it becomes a conjugate base. So that means fluorine is a conjugate base. Why is it a conjugate base? Well, think about what fluorine would do. It's negatively charged, so if fluorine had to do something with a proton, it would accept a proton. Meanwhile, H3O plus becomes a conjugate acid because it now has an extra hydrogen it could give up. So whatever was my Bronsted-Lowry acid becomes a conjugate base. Whatever was my Bronsted-Lowry base becomes a conjugate acid. So it's important for you to be able to look at a reaction and identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate base, and the conjugate acid. Let's look at our bottom reaction. We had the Bronsted-Lowry base in NH3. That became NH4. That's now our conjugate, what do you think, acid or base? Well, it was a base, so now it's an acid. OH minus, on the other hand, came from water, and now it's a conjugate base. That should make sense. If you ever labeled OH minus an acid of any kind, you would know something was going wrong. Similarly, if you ever named H3O plus as a base of any kind, you would know that was going wrong. So we've introduced you to a fair bit of vocabulary on this page. Bronsted-Lowry acids and bases, conjugate acids and bases, and the idea that some compounds are amphoteric. Let's keep working with these ideas. All right, so one thing to keep in mind is how do you generate a conjugate acid? Well, we make it by adding an H+. So just like we saw in the previous slide, we generated conjugate acids from bases that have gained a hydrogen. And so that means, say we had H2PO4 minus, and we want to know what is the conjugate acid of that guy? Well, the conjugate acid is generated by adding an H. So we got to add a H, which would give me H3PO4. Now what's the charge? Well, before it was -1, and then I added +1 to it. And -1 plus 1 gives me 0. So that actually is a neutral charge there. Conjugate bases are generated by removing an H. So we see that H2PO4 minus can go to its conjugate base by dropping a hydrogen, HPO4. Since it lost something positive, it goes from -1 to now -2. And that's the conjugate base. All right, let's do a few practice problems with conjugate bases and acids in our Bronsted-Lowry and acid definitions. Okay, so these are both from the OpenStack textbook. And problem 8 says, what is the conjugate acid of each of the following? What's the conjugate base? Well, to generate the conjugate acid, remember that we add a hydrogen. So that would be H3S plus. It becomes positive because it gained a proton. So that's the conjugate acid. On the other hand, losing a hydrogen would make HS minus, the conjugate base. HSO4, similarly, if I wanted to make a conjugate acid, I add a hydrogen and it becomes H2SO3. It's neutral because it was -1 and it gained a proton. All right. If it loses a proton to become its conjugate base, it's a HSO3, and now it's 2- because it's lost something that was positive. Okay, last little problem here before we wrap up this lesson. Identify and label the Bronsted-Lowry acid, its conjugate base, the Bronsted-Lowry base, and its conjugate acid in the following equations. All right, so what we want to think about is what of these is gaining a hydrogen and what's donating. Here we see that we have HNO3, and then on this side, NO3 minus. So what's that NO3 done? It's lost a hydrogen ion. It's donated it. So since the hydrogen ion was donated from HNO3 to water, we know this is our Bronsted-Lowry acid, and this is our Bronsted-Lowry base. That means that water over here that gained a hydrogen is now the conjugate acid. Remember, whatever was the base becomes the conjugate acid. Whatever was the acid becomes the conjugate base. So HNO3, which lost the hydrogen, now becomes a conjugate base. Another way to remember this is that the conjugate acid should always have the higher charge, and the conjugate base should always have the lower charge. So we go down to the bottom and we see Cn minus plus H2O goes to HCN plus OH minus. Well, now we see that what's happened is my Cn has actually gained a hydrogen, so my hydrogen was transferred from water to Cn. That means that my Cn is a Bronsted-Lowry base, something that's gaining a hydrogen. My water is donating a hydrogen, it's acting as a Bronsted-Lowry acid. And that means that Cn minus, once it gains the hydrogen, is going to give me a conjugate acid. Notice it also has the higher charge. Its charge is 0 compared to -1. Lastly, OH minus, which came from the Bronsted-Lowry acid, is the conjugate base. Okay, so that is the Bronsted-Lowry definition of acids and bases. And it's really useful as you go and start thinking about titrations and buffers, which is something that you typically get into after this. Thanks for watching this episode of Real Chemistry. You can subscribe or ask any questions you have down below.